Hey everybody, welcome back. We are in Unit 10 of AP Calculus AB. This is Lesson 2. We are rounding it out. We are finishing it up. We're on the home stretch. Let's keep it going strong. Today we're going to be looking at volumes of solids with known cross sections. This is a little bit strange at first because we're moving into 3 dimensions, but if you can wrap your head around it, this is a really cool thing. And hopefully it makes sense. So I want to look first at Geogebra is an online geometry and graphing software, and they have wonderful resources where people have made really cool programs with it. There's a few out there that I made. I definitely did not make this one. But you can see the address here, or just search for volume with known cross sections. We've got a couple different curves that have been graphed here. I'm not sure which one this is, but you can go here and open it and look at the details of it more if you want. But it's going to allow us to look at volume. So we have the XY plane here. The X axis is in red and the y-axis is in green. And so this gray thing here is the xy plane, and we've graphed like we've known to it. But we need to imagine that coming out of this plane is the z-axis. And if we say that this little purple line, which is the difference between the y-coordinate on the red curve and the y-coordinate on the blue curve, if we say that that's actually just one side of a square that comes up out of the plane, we can generate a solid, a 3-dimensional solid. This is showing one rectangle, and I can, move this to different places, and you can see that at each specific location, the square is a different size, and shrinks down to nothing. So this actually makes a real solid. And as we increase the number of rectangles, we start to see this, or squares as a case maybe, you start to see this figure get drawn out and filled in. And it ends up making this really cool little like hump formation that has these two edges, but the top of it is actually quite smooth and round. It's not pointy, despite these two kind of edges. So it makes this kind of a neat dome-like shape. And we can explore and look at it in different ways. So I really advise you to check this out and play with it. But as I change the shape that we use from, say, squares to equilateral triangles, now we have more like a thin. And then the ever popular semicircle, which I actually find very annoying to do the math on, and I'll show you why, but it's very common. And another common one that's not an option here is to actually do rectangles with known heights. So we can get like a flat figure or a figure that is, related some other way. All right, so that the semicircle is a really cool one, isn't it? Almost looks like the top of a fish that's coming out of the water. All right, so I'd like to start by not doing a full problem, but by doing an estimate of it, and maybe we can build up our intuition. So bear with me on just a second, for just a second while we build up to the full formula. So a solid shape with a base formed by the region bounded by x equals 0, y equals negative x squared plus 4, and y equals 0, has cross sections parallel to the x-axis in the shape of squares. So that's what we're dealing with. We're dealing with a parabola that I've shown here, and you can see it's defined this region right here in this little corner. And we know that the real shape, if we were talking about just cross sections, so I'm not saying it's made by rectangles, I'm saying anywhere you slice it, the cross section is a square. Well, we can estimate that by looking at making several different prisms. So starting right here, okay, oh, got the wrong thing on. Starting right here, I'm going to create this rectangular prism where this face here that I'm tracing, this face is a square. And we know that the area of a prism is length times width times height, or another way to say that is the area of the base times the height. Well, this is the big capital B base, and this is the height. Well, if we're going to be using 4 rectangles and we're going from x equals 0 to this intersection with the x-axis at 2, then I'm going to have to make each one of these 0.5 so that I can go from 0 to zero point 0.5 to 1 to 1.5 and then all the way to 2. And you can see how these prisms actually change in size as we move. And I'm using a left in point approximation, if you will. All right, so let's go through and do that and figure it out. So the first rectangle has a height of, looks like 4, but I'm just going to call it this. I'm going to say that this is f of 0 and squaring it because it's an area of a square. The height, this side here is, this side of the square is the height of f of x, and then same coming out of the paper up in the air is the square the other side. So that's why I said f of 0 squared. And then I'm going to be multiplying that times my height of my prism, which is that change in x, 0.5. And then we're going to do plus f of 0.5, that's the next x value, squared, times, again, 0.5. And then f of 1 squared times 0.5. And then lastly, f of 1.5 squared times 0.5. And so this ends up being 4 minus 0 squared times 0.5 plus 4 minus 0.5 squared times 0.5 plus 4 minus 1.0 squared times 0.5 plus 4 times 1.5 squared times 0.5. And I'll let you type that in a calculator and go ahead and estimate the volume and see what you get. It won't be the real volume though, because we should be using smaller divisions. So let's take a look at another one. What if we're going to do this with 10 of these? Well, if we were going to be doing it with 10 of them, then since we're going, our base has the entire curve of the region, the region formed by a curve has an x value starting at 0 and ending at 2. If we're going to do 10 of them, each height will have to be a 0.2. So I would have to do f of 0, and again, remember they're squared, so it has the area of this square here, and I know it's covered up by the second one. That whole area is the length from here to here squared times 0.2. But you know what I'm going to do? I'm just going to say 0.2 times the whole thing. So then I'll be doing f of 0.2 squared plus f of 0.4 squared plus f of 0.6 squared plus f of 0.8 squared plus f of 1.0 squared plus f of 1.2 squared plus f of 1.4 squared. I know this is a little bit tedious. Don't worry, they don't make you usually do this on the AP exam. This is just for discovery. 1.6 squared plus f of 1.8 squared, and then the next one would end it. So that whole thing should give us a better approximation for this volume, right? So my question is, how could we get an even better approximation? So that's, how could we find the exact volume of this? And I want to talk about how I would do that, but I want to look at this. Well, this is our change in our x values. It's the height of each one of our prisms, right? These are the bases, the capital B area are bases, and these are our heights. But if I factor it out, this is the change in x, what I call the delta x. Well, if I take a limit where I send that to 0, then it becomes the dx. So there's our dx. And this here was simply f of x squared. So we can simply use an integral of the area function squared. So let's write down that formula. The formula is going to be the integral from a to b of whatever the area of our base of our prisms are, which is a function of x. I was saying area of x squared. I'm sorry. The area function is f of x squared. So in this case, that's f of x squared. But it's just whatever the area formula is times dx. Very simple formula. So that being said, let's write an integral expression for the volume of the solid with the base formed by the region bounded by x equals 0 y equals 0, and y equals x squared, negative x squared minus 4. It has cross sections parallel to the x-axis in the shape of squares. Using the Geogebra application, I was able to create just a couple of examples. Here's that with 10 cross sections, but we're going to do it with an infinite number of infinitely thin ones. We'll be integrating from 0 to 2. Since they're squares, that's going to be f of x squared dx. So the integral from 0 to 2 of 4 minus x squared squared dx. That is the formula for the true volume of that solid. And there, I've shown you one with 50 of them. That makes it even more clear what it is. It is asking us to go ahead and evaluate that integral. I'll put it up here. Let me get my calculator back out. So turn that on. We'll do the integral of 4 minus x squared squared with comma x, comma 0, comma 2. 1.02.4. Wait, did I type that in right? Oh, that's why I always check the pretty print. I'm missing a minus. 17.067. All right. So let's look at a more normal AP question example. So we'll take a look at how to just find these answers. Set up the integrals needed to find the volume of the solid whose base is the area bounded by the curves y equals x squared and y equals negative 2x plus 3. So y equals x squared, we know that's just our parabola parent function. 2x plus 3 will be a line going through 3 and something like this. Let's find where they intersect. I'll just solve these two equations next to each other like that. So I get x squared plus 2x minus 3 equals 0, x minus 1, I think, and x plus 3. So this would be at my negative 3, and this is positive 1. We're going to do note that these are cross sections perpendicular to the x-axis. That's an important thing to note. If they're perpendicular to the y-axis, we need to use we need to be working with y as a function of x as a function of y. We need to be working with y and dy's there. All right, so rectangles with a height of 4. So I'm going to draw one representative. I usually even try and draw it with a perspective, and then I kind of bring it out over here. So this is my one cross section, okay? The height of this rectangle is going to be found by subtracting the y coordinate from the line minus the parabola down below. The height of this rectangle is actually a set 4, and if we make it into a prism, we're going to make this would be the area of the base, and our prism height would be the dx. So we find the area of this rectangle, which is, we said, negative 2x plus 3 minus x squared. And we multiply it there. Oh, I forgot to multiply it by the height. The height is 4. So remember, the formula is the area as a function of x times dx. So my area for each one of these cross sections is the height of the rectangle times the base of the rectangle. Base times height, and then to make it a prism, I multiply by dx. We'll be integrating from negative 3 to 1. All right, let's try the next one. That's all we do is set up the integral. We've done it. Okay, now we're going to be doing semicircles. So instead, let me just kind of redraw this again. So similar thing, we're going from negative 3 to 1. But now each shape is actually a semicircle, like that. So let me zoom in on that so we can see it. So the reason why I don't like the semicircles is I just feel like you have to divide by 2 too many times. So we actually need to get the area of a circle and divide it by 2 to make it half of a circle. But what is the r? How do we find the r? Well, the r is not this entire length from here to here. That'd be the diameter. It's just this. It's just this length here. It's half the diameter. So I actually have to take the difference between this y-coordinate and this y-coordinate and half it. So this is going to be the integral from -3 to 1 of, here comes the area of the circle, pi r. How do I get the r? Well, I got to take the top y-coordinate, which was the line. I think it was, what was it, -2x plus 3? Yeah. -2x plus 3 minus that y-coordinate, which is found with x squared. And I got to divide that whole thing by 2. Then I've got to square this because it's pi r squared, right? But then I got to divide that by 2 as well because it's only half of a circle and multiply by dx. So it's, a lot of people forget one of these divide by 2's. Make sure the first one is with your radius inside the squared. All right. I do have some practice problems for you to do. I'm gonna have you do this one practice problem. It's a little bit tricky because you actually need to write 2 equations for the x squared plus y squared equals 9. That's a circle. So solve for y, and that'll give you one function and another function with the plus or minus. All right, let's see how you did. So if you solve this for y, you should get y squared equals 9 minus x squared. So y is equal to plus or minus the square root of 9 minus x squared. So that's going to be a circle with a radius of 3. The plus part gives me that. So this is y equals the positive square root of 9 minus x squared. The bottom portion gives me y equals negative the square root of 9 minus x squared. I'm going to be using equilateral triangles, and we were given the equilateral triangle formula here, which is nice. So it's going to be coming out like that, where each side is the difference between this and this. So I'll be taking the integral from -3 to 3, the endpoints of the circle, of the square root of 9 minus x squared minus negative the square root of 9 minus x squared. So it ends up being just 2 times the square root of 9 minus x squared. And we're going to be squaring that, multiplying by the square root of 3, and over 4. And that whole thing is times dx. And luckily, we don't have to do anything with that. We just had to set it up. All right, let's take another problem. The base of a solid is bounded by y equals x squared, y equals 0, and x equals 2. But for this solid, each cross-section is perpendicular to the y-axis. So I need to be working with dy's. Y equals x squared is a parabola. Y equals 0, of course, is just this line here. And x equals 2 is here. So this is 2 comma 2 squared gives me a y value of 4. This here is 2 comma 0, and this is 0, 0. So this is the region that we're talking about, but we need to express these in terms of x as a function of y. Well, x equals 2 is already x as a function of y, because it's x equals. But I need to handle the y equals x squared, take the square root of both sides. And technically, I would need plus or minus, but we're looking at just positive x values, so I'll take just a positive square root. So the formula is the area as a function of y dy. So the function of y, I need to be making squares. So let's draw one representative square from here to here. And if I zoom in, this is the square coming out. The width of this, or the height of the prism, is actually going to be dy. But this is the difference between this x-coordinate and this x-coordinate. So this x-coordinate over here is x equals 2. So it's 2. Then minus this x-coordinate, which is the square root of y. And then, of course, the height is the same thing. So we'll be doing the integral from my y-coordinate 0 to my y-coordinate 4, from 0 to 4, of 2 minus the square root of y squared dy. And that's it. All right, I've got a practice problem for you. I think this is our last one, but it's got 4 parts, A, B, C, and D. So pause the video and give it a try. All right, let's see how we did. Y equals 3x is going to be a line like this. Y equals x squared is going to be a parabola. They'll intersect at 0, 0, and then somewhere over here, You could probably just figure it out that 3 times 3 is the same as 3 squared, so 3 comma 9, 0 comma 0. We draw the figure, and we're shading the region, the bounded region. Let's shade it. It's right here. All right, now set up and evaluate an integral expression for the area of the region bounded. Well, we're going to just simply subtract the top curve, which is 3x, minus the bottom curve, dx, and I'll do it from 0 to 3 if I'm working with x's. Next, it says the region R is the base of a solid whose cross-section is perpendicular to the x-axis, so I'll be using dx's because perpendicular to the x-axis means up and down, that are squares. So this just could not be easier. I'm just going to take exactly what I wrote a second ago, 3x minus x squared, because that's the difference from here to here, okay? And square that because it's a square, and then multiply it by dx to make it a prism. And we'll be doing that from 0 to 3. All right, on the next one, though, this time they are perpendicular to the y-axis and they're semicircles. So let me redraw the shape here. And this was 3 comma 9, and this was 0 comma 0. So I need to solve, again, y equals x squared becomes the square root of y equals x. Y equals 3x becomes y over 3 equals x. My semicircles are going to be like this. My radius, though, is only half of that distance. So my radius of my semicircle is going to be this outer far right version, which is the square root of y, minus the left curve, which is y over 3, and then that whole thing will be divided by 2. So our integral is from y of 0 to y of 9, because we're using y's, pi r, the square root of y, minus y over 3 over 2, pi r squared is the area of the circle, divided by 2 to make it a semicircle, dy. And that is it for volumes with known cross sections. I will see you in the next lesson.